All right, let's get right into it. For the past couple of years, we've all gotten used to this idea of AI thinking out loud. But what if that was just a temporary phase? Because we're about to look at a series of absolutely groundbreaking papers, all published in a single week, that point to a massive shift in how AI actually thinks, moving beyond words into something, well, something much, much deeper.
So this is the core question, right? Right now, if you want an LLM to solve a tough problem, it has to write out this whole long story for itself, a chain of thought, just to figure it out. And yeah, it works. But let's be honest, it's slow, it's clunky. So the big what if is, what if it could do all of that hard work internally, silently, and just give you the final answer?
You know, to really get where we're going, you have to appreciate where we've been. For the last 3 years, this whole thinking out loud thing has been the only game in town for complex reasoning. It got us this far, but it's pretty clear now that it's becoming a huge bottleneck.
And this really lays it all out. On one hand, you've got chain of thought. We all know it. It's wordy, it takes forever, but hey, it gets the job done. On the other hand, you have this new idea of silent reasoning. The dream here is to get all the smarts of the step-by-step process, but with the lightning speed of a direct answer. This isn't just a minor tweak, it's a completely different way of imagining how an AI can think.
Okay, so this brings us to the first massive breakthrough. A team from the University of Virginia drops a paper that basically proves reasoning isn't just something an AI does, it's a specific state of mind that it enters. And the incredible part? They found that state and they figured out how to turn it on themselves, manually.
And you have to appreciate just how fast this all happened. I mean, look at these dates. We're not talking months apart. We're talking about a cascade of discoveries all happening within a few days. It's a huge signal that the entire field is zeroing in on this one powerful idea at the exact same moment.
So, how in the world did they pull this off? Well, let's break it down. First, they basically hooked up an EEG to the AI's brain, recording its internal state when it was thinking step by step, versus just giving a direct answer. Then they used a special tool to untangle that messy signal. From there, it was detective work. They compared the two brain scans and hunted for that one specific signal that only lit up during deep thought. And then, the final, crucial step. They figured out how to hotwire the model and just flip that switch on whenever they wanted.
Now that special tool has a name. It's called a Sparse autoencoder, or an SAE, and this prism analogy is just perfect. Think of the AI's internal state as a beam of white light. It looks like one thing, but it's actually a jumbled mess of thousands of different signals. The SAE is the magic prism that splits that messy light into all its individual colors, and suddenly you can see them clearly. A feature for grammar, one for facts, and the one they were looking for, a feature for logic.
So this is the magic trick. It's a technique called latent steering. They'd give the AI a hard problem, but without telling it to think step by step. Normally, it would just fail. But this time, right as the model began to process the question, the researchers would go in and mathematically crank up the value for that one little reasoning feature they found. It's literally like flipping a switch in its brain, forcing it into a deep thinking mode, and suddenly, it just solves the problem.
And the results are just, look at this. They're stunning. On a standard math test, just asking the model for the answer gets you a pathetic 24.5% accuracy. The old slow chain of thought method, that gets a pretty good 79.3%. But look at that middle bar. That's the steered model. Just by flipping that one single switch, its accuracy skyrockets to 73.3%. It's almost as smart as the slow method, but with the potential to be insanely fast.
Okay, so that's piece number one of the puzzle. We can find a reasoning mode and turn it on. That brings us to our next paper from UPenn and Microsoft, which asks a really fascinating follow-up question. What if the AI didn't have to pick just one line of thought? What if it could explore multiple possibilities at the same time?
And that's such a powerful idea. Think about how an AI works now. It gets to a fork in a road, maybe it has to decide whether to add or multiply two numbers. It has to pick one, and if it picks wrong, well, that's it. Game over. The whole rest of the solution is garbage. This new paper is about letting it explore both paths at once.
They call this multiplex thinking, and the analogy they use is great. Instead of the AI's internal thought being a single note, like the word multiply, it becomes a musical chord. This ghost vector, as they call it, doesn't represent any single word in English. It's a mathematical superposition that holds the concepts of multiply and add, and maybe even subtract, all at the same time.
And this is the perfect way to frame it. Schrödinger's token. The model carries on for a few steps, holding these parallel realities in its mind. Then once one path starts looking more promising, the other possibilities just collapse. And what's left is a single correct line of reasoning. It's like the AI gets to explore multiple futures before it has to commit to one.
So what's the big deal? Why does this matter so much? Well, it turns out the internal bandwidth inside an AI's mind is massive, and we've been barely using it. The old way was like sending a tiny little text file down a huge fiber optic cable. This new method is like sending a compressed zip file packed with tons of different ideas. It's just a wildly more efficient way to use the AI's own thinking space.
Now, I know this all sounds a bit theoretical, with ghost factors and whatnot, but this is where it all gets very, very real. Our third paper, from NVIDIA, takes these ideas of silent, compressed thinking and applies them to robotics, where every millisecond counts.
Here's the problem NVIDIA was facing. With chain of thought, if you tell a robot to pick up a mug, it first has to stop and write itself a 200-word essay explaining exactly how it's going to do it. In the real world, that kind of delay makes a robot completely useless. By the time it's finished its little essay, you've already picked up the mug and finished your coffee.
So what was their solution? You guessed it, they used this new silent compressed method, and the result is this one incredible number: 30. A 30 times compression factor. They figured out how to squash that entire 200-token essay down into a tiny, dense little package of pure thought.
And this chart just shows you the insane difference. The old text-based plan requires this huge data blob of 800,000 numbers to represent the idea. The new latent plan takes all of that same meaning and compresses it down to just 25,000 numbers. It's the same thought, just represented in a way that a machine can understand and execute almost instantly.
Okay, let's just step back for a minute and put this all together. Because the really amazing part isn't just any one of these papers. It's how all three of them, published in just a few days, snap together like puzzle pieces to show us a new picture of how AI can reason.
It just fits perfectly. The first paper from UVA found the on switch. They proved a reasoning state even exists. The second paper from UPenn and Microsoft showed that this internal thinking space has the capacity to think in parallel. And the third paper from NVIDIA proved it has the density to compress really long thoughts. State, capacity, and density. It's the whole package.
And this all leads us to the single most important takeaway. If you remember one thing from this, make it this. The fundamental unit of thinking for an AI is not the word, it's not the token, it's the latent configuration, the entire specific pattern of activation, the whole shape of the thought inside the model's mind. The implication here is just profound. We're watching AI shift from being a really clever manipulator of language to being a manipulator of thought itself. The words we type and the words we read back are just becoming the user interface. They're the keyboard and screen for much deeper, much more efficient, and maybe even alien kind of thinking that's happening silently underneath it all. And that leaves us with one last kind of mind-bending question. If AI is developing its own silent language of thought, a language built for machines, not for humans, what kind of things will it be able to figure out? What new problems can it solve that we, stuck with our slow word-by-word language, don't even have the ability to properly ask?